This section covers the analysis of relationships. This is the second most important part of creating an information specification, hence the name Entity Relationship Diagram. In this section, we'll identify how we find relationships between any two associated entities and model them on an entity relationship diagram. Remember, an entity relationship diagram simply declares the business entities and their relationships graphically. Here's what we'll cover in this section: definition of a relationship, modeling meaningful relationships, discovering business relationships, naming relationships, representing relationship cardinality, relationship type and occurrences, eliminating data redundancy through relationships, relationship connection rules, capturing compound relationships, and a sample relationship specification. First, my definition of a relationship. This is one I've used for many years, although there are other similar definitions in the technical literature. A relationship is a named association among the occurrences of two or more entities or two or more occurrences of one entity. That last part of the definition is easily stated with the example that an employee may be married to another employee. Relationships result from business policy processing or situations. The main point I want to make here is regarding that last sentence. It's the business policy processing that determines the relationships we want to capture on our model. We represent a relationship with a diamond symbol. We can also support the relationship with the relationship specification. These are used to support entity relationship diagrams, also abbreviated to the acronym ERD, but may be optional if the entity relationship diagram can model all the necessary data characteristics. The relationship specification can contain the relationship name. This must be a unique name on our model. It can get quite interesting trying to create unique names for relationships. Its role in the business, that is, why do we have this relationship? Cardinality between entities, in other words, one-to-one, one-to-n, or n-to-n. Connection rules, in other words, which entities may be connected to this relationship. We can also document the events that create, form, or sever this relationship. Note that we may keep both entities but delete a relationship. For example, we may move an employee from one project to another, and both the employee and project are still around, but we sever one relationship and form another. We actually call a modeled relationship a relationship type, because it typically represents many occurrences of a relationship. I use the diamond symbol to represent a relationship, but I mentioned in the previous section that there are other methodologies that use different symbols. I will show another symbol type in this section. I've seen many authors, myself included, advocate new symbols, but try not to get adamant about specific symbols in information analysis. Just make sure they're constant within an organization, therefore making it readable to all those who need to interface with the model. We want to model meaningful relationships. Relationships are necessary associations among the entities identified in the business. So one aim would be to develop the minimum set of meaningful relationships required to accomplish the necessary business processing. Arbitrarily creating a relationship between every entity on the model is probably excessive and would not produce a good model of the business needs. In fact, the relationships on the model will be implemented, so there's a cost to implementing them. I like to think of a manual implementation of relationships such as index cards. The more cross-references between entities we need, the more index files we need. We're trying to capture relationship business rules, so we don't want to clutter up the information model with relationships that simply show all possible combinations of conditions between entities. Also note that relationships are not intended to show access direction between entities. We can use an access path diagram, which we'll talk about in a later section for that. How do we discover business relationships? Well, we discover relationships by capturing verbs. Well, not all verbs. Identify verbs that relate to entities or more than one occurrence of an entity. I'll show an example of relating two or more occurrences of an entity later, but first let's talk about relating two separate entities. Once we know what things, entities, need to be stored in the business, we look for how they are related. For example, a member of the business staff may say, typically a seminar is sold to a client to be conducted at their premises. A student who works for that client then enrolls in that seminar. I've shown a preliminary entity relationship diagram result on the right here, where the verbs from the business statement have been used to form relationships between entities. We can also find out from existing records and files how any sets of stored data are related. For example, look for index cards or local computer spreadsheets and contract lists linking two sets of data that are now recognized as entities. We can even find relationships by seeing that two columns are associated on a report. For example, parts and their locations as two columns on a report. I like to look for compound keys needed for access to a record. For example, if I need an employee name and a project name to get to billing hours, then there is probably a relationship between employees and projects. Model your result with a named relationship diamond symbol. The problem we have at this point is these relationships will probably be stated as unidirectional. For example, a seminar is sold to a client, but of course a client is not sold to a seminar. So this leads to the issue of naming relationships. We can show the bidirectional association between the same two entities by adding more relationships. For example, we can add a buys relationship to our previous example. Now our model segment states that a seminar is sold to a client and a client buys a seminar. So we can have multiple relationships between entities. I've shown on the right another style for depicting these same relationships. With this model, we read the relationship connecting line in a clockwise direction, meaning from left to right over the relationship line, and then from right to left below the relationship line. It reads, a seminar is sold to a client, and a client buys a seminar. Or, back to our ERD example, we can name the relationship so it reads suitably in both directions, and specify the different relationships in a relationship specification. On the right, I've named the relationship seminar buying. And now we can say that a seminar is involved in a buying relationship with a client, and a client is involved in a buying relationship with a seminar. We can document a relationship specification for seminar buying, detailing the different associations of the entities. I'll show a sample relationship specification later in this section. Now let's talk about representing relationship cardinality. We identify the cardinality of entities in relation to other entities in a relationship. In other words, the ratio of an entity to another. One to one, one to many, or many to many. On an ERD, cardinality is indicated with a number 1 or an N next to the entities as shown. Here are two examples of an ERD. Sometimes you'll see a circled cardinality indicator. That's known as an anchor point, and it's the start point from which we read the relationship. Anchor points can make the event-oriented information model more readable. The top example reads, one instructor is involved in a teaching relationship with many seminars. Or we can say an instructor can teach many seminars. The bottom example reads, one seminar is involved in a teaching relationship with one instructor. Or we can say a seminar is taught by one instructor. On the right, I've shown another style model showing the same example of instructor and seminar, but with what's known as a crow's foot symbol indicating a many relationship. Actually, it indicates a potential of many, so it really indicates 0, 1, or many. I don't know if I want to admit this, but I've been reading books, writing and creating seminars and teaching on the subject of information analysis for 3 decades, and there's a lot of symbology out there to choose from. I prefer to make any analysis models as uncluttered as possible and let support specifications fill in the business rule details. However, if you want to put more on the model, there are additional symbols out there. For example, we can specify more cardinality rules graphically or put these in a relationship spec. The lower right models show more modeling symbols. The top small model reads that an instructor can teach many seminars, but a seminar can be taught by one and only one instructor. The lower model shows a public seminar can have 0, 1 or more clients associated with it. In my business, this is true at any point in time. When I schedule a public seminar, I don't know if any client is going to sign up for it. Finally, I've shown yet another example of cardinality symbols, a line between any two entities with a single or a double arrow on it to indicate a one-to-many relationship. If you work for an organization that has already selected a methodology using a specific symbol set, then of course use that one. However, the concepts I'm teaching in this tutorial still apply regardless. Before going further, let me clarify a relationship type and its occurrences. I made a similar comment in regards to entities in the last section. For clarity, we must be careful to distinguish in our minds between a relationship type and its occurrences. First, I want to let you know that I think of relationships as invisible strings between entity occurrences. I do this to remind myself that a relationship is really a relationship type, and there are typically many occurrences of the relationship in the real world. Here's an example. If at a point in time a student could be signed up for many seminars, and a seminar can have many students signed up for it, then a segment of our model would reflect that as shown. Notice the example shows a many-to-many situation. For those database people watching this tutorial, this is analysis, not design. We show many-to-many relationships on our analysis models. In the real world, the actual occurrences of relationships and entities may look something like the diagram on the lower left. In this sample, the student Jones is signed up for 2 seminars, and Lee is signed up for 3, and the Business Info Analysis seminar has them both signed up. The red dashed lines are my invisible strings I mentioned earlier. I said in the definition at the beginning of this section that a relationship could associate 2 or more occurrences of one entity. Here's an example. The ERD may look strange, but it's valid. It states that a part can contain many other parts. In the actual occurrences view, we can see that an engine can have other parts such as a distributor, starter, and alternator, etc. As a computer person, I like to remind myself that an information model can be implemented in a manual environment as well as a computer environment. So in the design stage, relationships can be positions of documents in a file, for example, order forms within a customer folder, customer ID sheet, customer index cards, or pointers in a computer database. Remember, in information analysis, we aim for zero redundancy in the model. Identifying and separating out relationships helps us achieve that goal. Here I've shown an existing manual implementation of file folders where the project folders contain project data and a list of employees assigned to this project. It also has some information about the employee in the project folder, no doubt duplicated here because it is information that is always convenient to find quickly. Also, the employees folder contains employee data and a list of the projects that this employee works on, again with some additional data about the projects, probably for the expediency of data access to this duplicated data. Now, there will not only be masses of data duplication, redundancy, but tedious and error-prone update problems between these 2 folders. However, as shown on the lower diagram, if we keep the information for a project and an employee separate, that is, in separate entities, and then link the entities with the relationship, the data duplication redundancy goes away. Then when the model is implemented with the entities separate, there will be no data redundancy or update problems in the final files. I'm trying to show a 3-dimensional problem with a 2-dimensional graphic here, so don't let this graphic mislead you. The important thing to note is it's the relationships that brings the data in the entities together. Of course, we need to specify the actual connections and cardinality of these relationships. We'll talk about this later in this section. Now, on a similar note regarding relationships, we should connect the relationships to the correct entities on the model. In the example on the right, the requisition entity, which is an associative entity between supplier and material, points to the supplier for that requisition via a relationship. The requisition also has the dependent entity for the line items on that requisition, and those line items point to the material that is referenced on the line items via relationship. And a relationship is used to identify the materials from the supplier for the requisition. If we allowed a repeating group within the requisition for the line items, we could show a 3-way relationship between requisition, supplier, and materials. More on compound relationships later. As you can see from this small example, an information model for the whole organization can get quite complex. So we recommend doing entity relationship diagram fragments or event ERDs for simplicity. Again, I'll talk more about this in a later section. Something else we can show on an information model is relationship connection rules. We can capture more specific business rules on the information model such as whether a relationship between entities can have mandatory or optional connections. When modeling the relationship, look at each entity and ask, must it always participate in the relationship? If not, class the connection as optional, otherwise as mandatory. Here's a member of staff stating, when a client contacts us and asks us to put on a seminar just for them, we'll schedule an in-house seminar. The analyst may then say, so an in-house seminar must be associated with a client, but do all clients have to have an in-house seminar associated with them? Which may elicit the staff response, no, of course not. We can show these connection rules graphically on our model or state them in the relationship specification. The business rules are, every in-house seminar must be associated with a client, so the in-house seminar connection is mandatory. And a client does not have to be associated with an in-house seminar, so the client connection is optional. We can show these connection rules graphically, as shown on the model on the right. The dashed line to the relationship indicates an optional connection, and the solid line indicates a mandatory connection. Here's a cautionary point regarding what I call organizational connection rules. This kept messing with my brain when I started creating information models. Be careful with connection rules. When we observe a specific event process to form a relationship, the cardinality can be different than when we view our model at any point in time from an organizational point of view. By the way, LCI believes business data rules can be event specific. Looking from the point of view of an event, where a client buys an in-house seminar, the client and the in-house seminar connections are both mandatory, meaning client and in-house seminar must both be connected to the relationship. The model on the right depicts this. However, if we looked at our model from an organizational, any point in time view and asked, what is the relationship of a client to an in-house seminar, then we would probably say a client may have 0 or many in-house seminars associated with it. So the client connection is optional. In other words, not all clients have an in-house seminar schedule. Notice the same two entities with differing connection rules. Now we can put multiple connection relationships between the same two entities on our model as shown, or we can create one relationship specification stating these differing rules. Investigating connection rules can bring to light entities, supertypes, subtypes, and of course nails down detailed business rules for an organization. One thing I like about the entity relationship diagram is the ability to put compound relationships on the model. If we want a complete relationship view, we need more than a binary relationship structure. We need an n-ary relationship structure. Suppose we have a staff statement, a client will enroll many students in an in-house seminar. For this example, we can model a three-way relationship. This ERD brings together the real situation where one client buys an in-house seminar and associates many students to it, rather than modeling separate binary relationships as shown on the right here. Now we can state the connection rules for the relationship in-house buying in a relationship specification. Finally, let me show a sample relationship specification for the in-house buying relationship shown in the previous example. Please note I'm going to specify what I call the event view, not the organizational view of the relationship. We can be specific in documenting relationship from a process event point of view. We can name the relationship based on the event and be specific about the connection and cardinality rules for the event. At the event level, the ERD allows us to accurately specify the n-ary relationships. Obviously, we should state the relationship name and maybe the date of the specification. Then identify the role in the organization. In other words, why do we have this relationship? I've entered this relationship identifies the client to which an in-house seminar is assigned during a sales event and the students that are assigned to the seminar at that time. Then I have shown each entity's connection rules and cardinality rules in separate columns. For example, a client has a mandatory connection to this relationship. Note this changes for the organizational view to optional. And the cardinality rule for this entity client to other significant entities in the relationship. One client is associated with one in-house seminar. In other words, a one-to-one relationship. Again, note that this changes for the organizational view to one-to-n relationship. Next, the entity in the in-house seminar has a mandatory connection to this relationship, and the cardinality rule is one in-house seminar is associated with one client. In other words, a one-to-one relationship. Again, note that this changes for the organizational view to N-to-1 relationship. The third entity, student, has a mandatory connection to this relationship, and the cardinality rules are at least one and maybe many students can be associated with one in-house seminar for one client. In other words, a 1 to N-to-1 relationship. I like to identify the events that create, in other words form, and delete, in other words sever, this relationship. So I've included two event names. Client wishes to buy an in-house seminar, and client wishes to cancel an in-house seminar. At this point, when I'm teaching a live seminar on information analysis, I ask the seminar students, where is this recorded in your organization? The room is usually quiet. That's the basics for relationships.